So good afternoon, ma'am and sir. So in this chapter, I'm going to present to you the methodology in our research. So in this chapter, the researcher will also discuss the design flowchart, the block diagrams, and the circuits that will be used to obtain the specified goals of this study. All the circuit design and layout will be done using the HVICE. So shown in the figure below is the process of the flowchart that our research will be following. Will follow. So first is we have the planning of desired specification, and the next is the designing of the architecture. And after the designing of the architecture, we have the pre-simulation. And after the pre-simulation is decide whether the specification have met. And this is a critical or the crucial part because we will we will reconsider all the things in architectures that we lack or that will give us the direction or the flow that we are going to take. So here are the also the we take into account into our research about the consider parameters that we need to consider or the considerations that we had to take into account in order for us to finalize our output. So first is we have the circuits that are operating in the sub-threshold voltages. So operating at sub-threshold level means that no voltage in the integrated chip rises above the threshold voltage. Operating circuit that supplies below 0.9 volts enables the circuit to have very power consumptions, provide sub-threshold currents. So another consideration we're going to take is also the MOSFET aspect ratio for the sub-threshold of operation. A high because this entails that a higher aspect ratio increases the current gain and subsequently a higher current for a given PG. The same is for higher M, that means N times the aspect ratio. And also, we take considerations of the technology that we use, and it is a 18 micrometer and a 65 nanometer process technology because also it will definitely affect the whole process because as technology progresses to smaller dimensions and lower voltage supply voltages, matching dominated circuits are expected to see reduction in power dissipation, whereas noise dominated circuit will see an increase. So we'll proceed now to the implementation of BGT based temperature sensors. So shown in figure 3.5, BGT based temperature is the architecture or basically the conventional architecture that produces the stated voltage or the VBA. Integrated temperature sensors usually require the generation of a temperature-dependent signal and reference signal. Due to the characteristic of BGTs, these two signals can be easily generated. So as shown in the BGT-based temperature in figure 3.5, a transistor is biased by a current source and the voltage between its base and emitter is given by VB equals KTQ ln ICIS. So we'll proceed now to how we will generate the peak voltage. So the difference between two VBS is given by the change of the VBE is equal to the VBE2 minus VBE1. And we arrive at the equation Vt over Q times Ln N. So as a result, the process-dependent current is cancelled out. Ideally, the change of the VBE is proportional to absolute temperature or the PTAT. So this is figure 3.6 is an example of a resistor in series with diode that produces produces a peak voltages. And by choosing the value of R appropriately, V will be terminally stable. In other words, V may be made independent with respect to changes in temperature. So here, also talking about the analyzing theory and simulating open gap voltage reference. Specifically in 3.5.1 is how we generate the negative DC voltage. So the base emitter voltage of bipolar transistors or more generally the forward voltage of a p-n junction diode exhibits a negative TZ. We first obtain the expression for the TZ in terms of readily available quantities. For bipolar device, we can write IC is equal to IS exponential function of VBE over VT. where Vp is equal to Kp over Q. And how can we also generate the positive DC voltage? So if two bipolar transistors operate at unequal current densities, then the difference between their base emitter voltages is directly proportional to the absolute temperature. For example, as shown in figure 3.5, if two identical transistors IS1 equals to IS2 are biased at collector currents of NIO and IO, and their base currents are negligible. So, so after all these concepts introduced, so we finally get through the generation of the analyzed concept. So shown here is the conventional voltage bandgap reference using the analyzed concepts mentioned above. So we also did some simulations in order to test if the conventional conventional circuit that we choose will work. So here is the result of the simulation test. At the process technology 0.18 micrometer with a supply voltage 1.8, we obtained a small temperature coefficient of 0.6, 0.8 ppm, 0.0, 0.6 ppm sensitivity with a very low sensitivity to VDD 0.013%, max VREF of 1.2327, minimum VREF of 1.2325. And here is a block diagram of our proposed circuit architecture, which will be discussed by my group mates. So that's all. That's all my part. And again, thank you very much.